The purpose of this video is to introduce the ratio test as it applies to series. I will ask you to recall with me the geometric series. The geometric series takes on the following form. This is the sum from n equals 1 to infinity of a times r raised to the n minus 1 power. And it looks like the following. So we have a first term, and then going to consecutive terms after that, we'll be multiplying by this value r. We refer to r as a common ratio. Now with that in mind, the way that we deduce what the common ratio is we take the ratio of any two consecutive terms. Now by a sub n plus 1 and a sub n, I mean this expression that we would get when we plug in either n plus 1 or plug in n. So this would be a times r raised to the n plus 1 minus 1 power over a times r to the n minus 1. And a little bit of algebra lets us know that that is going to wind up being equal to r, which again we refer to as our common ratio. So the ratio of consecutive terms winds up being this value. Additionally, as long as that common ratio is between -1 and +1, the series converges. I shouldn't have written that with the or equal to signs on it. Now, it's for that purpose that we could also deduce the following. If I were to take the absolute value of this ratio and wind up getting r, the only thing that we would need is that r is less than 1. The reason that I bring this up is because of the definition that we gave for absolute convergence. The ratio test states the following. As long as eventually a series starts acting like a geometric ratio, then the series will converge. And by eventually, I mean the following. The ratio test says to evaluate the limit as n goes to infinity of the absolute value of the ratio of consecutive terms. If you evaluate this limit and you get a number, you are allowed to draw a conclusion based off of that number that you get. If L is less than 1, the series converges absolutely. If L is greater than 1, the series diverges. And if L is equal to 1, you are allowed to draw no conclusion, and you'll have to try a different test. Now, the ratio test is very handy in certain situations. So let's talk about the situations in which it is very handy. So the usefulness of the ratio test will be if the terms of your series or sequence contains the following. The ratio test will be the most useful anytime you see factorials. In fact, anytime you see a factorial, this is basically exactly what you want to do with it. This is due to the fact that if you have an n plus 1 factorial divided by an n factorial, which is what you would get from the term that we use for the ratio test, you can expand the larger factorial to look like the following. This will be n plus 1 times n factorial divided by n factorial, and the factorial reduces really, really nicely. This is also going to be very helpful if you have exponentials. Exponentials will be really handy because if you have a raised to the n plus 1 power divided by a raised to the n power, you can use algebra to reduce this very nicely to simply be an a. It's relatively useful for polynomials, simply due to the fact that if you have the same degree polynomial, they're going to wind up going to the wind up canceling out to be 1 as n goes out to infinity. And finally, if you have a variable to a variable power, this is kind of useful, just not particularly useful. There will be a different test that we use for this.